Okay, so hello everyone. Good morning, good evening, good afternoon. Let's start our next scientific seminar of Quantum Technology Center of Moscow State University. And first of all, I would like to announce the next talk. So next week, we will have a talk from Stanislav Straupe from our center. And it will be about quantum state engineering and tomography with high-dimensional spatial states of photons. And now we have a talk from Ivan Dyakonov, also from Quantum Technology Center, about linear optical platform for quantum computing in our center. Please.
Device 1 connected.
Okay. Welcome, everyone. Thank you for the introduction, Konstantin. So my talk will be devoted to the linear optical research held in the Quantum Technology Center. So the center is located in Lomonosov Moscow State University on the Faculty of Physics. So there is a main building in the center, which is quite large. And where is the pointer? So this is the mathematics faculty, and this is the physics faculty. And our lab sits somewhere over here in the corner of the screen. So our center was founded in 2017, and it covers a rather broad area of topics, including quantum communication, quantum computing, quantum optics. Also, we have an atomic laboratory working with single atoms and integrated photonics, which I will cover today. And also we have 2 labs on nanophotonics and metamaterials and single electron physics. So my talk will be mostly devoted to topics regarding the linear optical quantum computing, that is integrated photonics research, which is done in the lab, and also some theoretical achievements we have made during the past years. And Stanislav Straupe will cover another part of the quantum optical experiments held in our center, which are done with the optical or orbital angular momentum and B-photon states. So the main topic of our research is depicted over here. So linear optical quantum computing could be, in general, dissected into 2 different parts. The first one is a more or less near-term architecture, which everyone uses in contemporary experiments. So the photons here start at the very beginning of the circuit. Then we have some linear optical circuit in between. And in the very end, there is an array of detectors, some coincidence logic, and sometimes there is a feedback loop from the coincidence logic to the integrated circuit to modify the circuit regarding the algorithm which is being performed on this platform. So the more long-term architecture, which is proposed by Terry Rudolph and his co-authors from Bristol and London, and which is now developed in the PsiQuantum company, is depicted on the right side of the screen. So this one is a bit different because the photons generated here doesn't have to traverse the whole circuit like in the near-term architecture on the left. So this one is actually less prone, more prone to losses. So this approach really could be scalable potentially, and this is what the PsiQuantum tries to develop, I suppose. Because there is no particular info about their development so far, but this is something they have been developing during the past years, according to the publications. So in our lab, we mostly work on the near-term device right now. So we have some research regarding the single photon sources, but the most stuff is done for the middle part, the linear optical device here, which is depicted with the lambda letter. So I will try to pick different parts of the linear optical quantum computer one by one, and then we will discuss different approaches which we employ in our center to tackle the problems of the of both near-term architectures and the long-term one. So here on the slide, there is a unit cell of the long-term architecture device, and it's easier to underpin all the problems which we have to solve because these problems are actually common between the near-term architecture and the long-term one. So the first one is the photon source. So for this architecture, you need a 3-photon GHZ state, which is a highly entangled state. Anyway, to get these 3 photons, we need at least a single photon source and entangling gates of some kind, or, which is better, an entangled photon source on demand, which is sufficiently harder to get, but in principle, it should supply these 3-photon GHZ states. Next, the fusion gates, which perform the construction of the computational cluster in this model, require quite sophisticated optical circuitry and quantum number resolving detectors, both of which apply to the near-term architecture as well. Next, to construct the 3-dimensional cluster for the quantum computation, some low-loss delay lines have to be included into consideration because the machine, which was depicted on the previous slide, operates in a time-like manner, switching in and on different parts of the device. So the photons have to travel from one layer to another one with some time-like separation. And the last but not least, we need some high-speed electronics to process all the information about the successful operation of fusion gates, make decisions on which switches we need to turn on and off, and also we need fast optical switches, which I decided to make their own place regarding the optical circuitry. So these are the main, I would say, challenges have to be met to create the long-term device, but development in different fields of these are actually helping to implement the near-term device as well. So what we do in our lab can be divided into 4 different groups. So we have research regarding the optical circuits and the theory, which I will be talking today. The sources are now under installation and the development. So we have purchased a single photon source from the company Quandela. Nicholas Amaski is also here in this talk, and he gave a talk a few weeks ago. So we are also assembling a 10-channel demultiplexer to demultiplex the time sequence of a single photon pulses into different channels, independent channels. And also we have our own 6-photon SPDC source, which is actually quite a basic one, used in different labs, like for example in the Xiaxong MAS, which was shown us the previous seminar. And also we have a system of 24 single photon nanowire detectors, which are quite good. They are manufactured by Russian-based company Scontel. The quantum efficiency is around 95%, and they are now standing in the lab, working quite nicely. So today I will talk more about optical circuits. So we have some research regarding the design of the optical architectures, and also we work on the technology by ourselves using this femtosecond laser writing technology. And also we have a strong collaboration with Bauman Moscow State University regarding the lithography-based platform. And in the end, I will speak a little about how to optimize the gates for the quantum computer. So let's start from the technology side. So first, I would like to acknowledge our research with Bauman Moscow State University, which help us a lot with the nanofabrication of silicon nitride waveguides. We have began this research from scratch, so we didn't have any particular technology for silicon nitride a few years ago. And during the past year, we have developed, in collaboration with these guys, the technology to fabricate single mode waveguides with quite low loss operation, and also some coupling devices like grating couplers and edge couplers. All these are designed for 925 nanometer, which is the wavelength of our quantum dot single photon source provided by Quandela. That's why this wavelength is quite strangely developed here instead of, for example, telecommunication wavelength, which is more widespread. So these are the slides and the photos of the devices we have already made. So we are working now only on the passive ones, the directional couplers, wide splitters, optimizing the grating couplers, and also starting to work on active devices, thermo-optically tunable phase shifters, for example. So yeah, we have quite a lot of success working with Moscow State University. So if you want to contact them, there is a link over here. Our own technology is way simpler. It's quite known femtosecond laser written devices. So the principle of operation is depicted on this slide. You have the laser beam, which impinges a glass slab, and the glass slab is translated along the focal point of this exposure beam. So the exposing conditions are chosen to be quite mild, not to modify the structure too hard and not to break the glass, but the refractive index modifies slightly, helping us to create the core of the waveguide, thus translating the slab along this focal region. We can define the structure of the waveguiding circuit. Also, we can print like a lot of waveguides inside one slab, make them interact with each other by redistributing optical power between the waveguides, and also we can create thermo-optical phase shifters using this platform, which I will be talking in more detail on the next slide. So this is our setup. It has this enclosure, the housing, which helps us to prevent a little bit of dust getting in, and also protects our eyes because the laser sits on the very top of the plate over here where the laser pointer shows. So yeah, there is the beam right in front of my eyes, for example, when I enter the lab. So the schematics are the following. You have the femtosecond laser on top. We use fiber-based ytterbium lasers. They operate at around 10 megahertz repetition rate, which can be chosen using the computer-controlled stages. So the frequency doubled light of this laser is then forwarded towards the sample. Also, we have an active control of the power, which allows us to write these structures with a very precise and stable power tuning, which is quite good. For example, if you need to write a lot of waveguides at the same time without changing the conditions and keeping the parameters of the circuit stable during the operation. So here is a small video. I hope we can run it. Just a second. So for those who are not familiar with the technology, there is a video how it works a little. The video is done solely for demonstration purposes. There is actually a slab with metal on top, and we run some laser engraving routing here, which engraves the electrodes on top of this slab with metal. So, sorry. Regarding the waveguide characteristics, we have actually got quite good propagation loss, which is around 0.2 dB per centimeter for some regimes. But in general, we use a bit worse regime because we want to bend our waveguides quite strongly with, for example, 40 or 50 millimeter radius. So for that regime, the propagation loss is around 0.5 dB per centimeter. Also, the waveguides we fabricate have quite good coupling loss per facet because the size of this more optical mode is defined by the refractive index of the core, which is quite close to the optical fiber one. It's on the same scale, so the size of the mode matches nicely with the optical fibers. So the bending loss, as I said, are quite low for 50mm radius. So this is more or less a amenable regime for using it for our purposes. So what we actually aim to do with these devices now. So we wanted to build a thermo-optically tuned device, which could be employed further in quantum optical experiments, for example. For this purpose, we had to evaporate somehow the metal film on top. We found a group in our university who agreed to do that for us. So once we had the technology of the evaporation on this glass slab, we next applied the so-called ablation process to remove some of the material from the top of the chip using the same femtosecond laser. So we actually have some marks inside the chip which help us to realign it once the circuit with the metal layer is put back into the setup, and thus these thin wires which heat up our circuitry stand in the very place that they are designed to be. So we can do this with quite significant precision, around a few microns, which is not comparable to the lithography, of course, but keeping in mind that the size of this structure is actually on centimeter level, the precision is enough to create quite a precise layout of the electrodes. So what we have demonstrated with this technology is the 4x4 universal device, which looks like this. So we have a board on top, which we have a photo. So here we have it assembled. So the chip sits underneath the PCB board over there. The PCB has the control wiring, which is connected to the programmable current source, which is used to define the heating regions and the temperatures on different waveguides. And also the light is coupled here by the single mode fibers and the single mode fibers on the output either. And also have to thermally stabilize the whole setup, otherwise we cannot achieve stable performance of this heated device. So we actually did not perform the full unitary reconstruction of the matrix of the interferometer. We only made it work in the classical regime by fitting it to a given intensity distribution, which is given over here. We generate some output distribution, and then we try to run an optimization problem, which sets the phases on the chip in order to match the output distribution of intensity to the one we want to set. So if we generate these distributions arbitrarily, so these are some random distributions here, and this is the infidelity of the preparation of these distributions, the device works quite good. So the infidelity is, the average infidelity here is on the order of 10 to -3, which for the devices of this kind are quite good. So the time of switching is around 180 milliseconds because we want the whole structure to get stable. So all the temperature diffusion processes must stop before we measure the output distribution. This happens after something around 180 or 20 milliseconds. If you think about a single modulator, an optical modulator, it works way faster than the whole circuit. So if you have only a single Mach-Zehnder interferometer switched by the thermo-optical heater, then you have something around 15 millisecond time to switch from the very beginning to the almost very top state here. And also we tested the device in the switching regime when we had to flip, for example, the light from the first input to one of the outputs, even here, one of the 4 outputs. So this is like an extreme test for the device because it requires the best visibility of the interference in each Mach-Zehnder interferometer. So we can see that some of the interferometers inside the circuit doesn't work as expected, but most of them do, because the infidelity here is quite low. Okay, so next, during the past months, we have tried these devices with the quantum light. So the very easy, the most easy test is to perform a CNOT gate, a basic CNOT gate depicted over here. It has 6 modes. 4 of them are used to encode the qubits, and 2 of them are just the auxiliary ones to ensure that the operation is as expected. So on the left, you can see the truth table, which is actually not really the full process matrix, but only the probabilities of finding the logical states on the output. So the truth table fidelity is quite good, 96%. And also you can see here that the truth table has the values of 0.11 approximately, which is the probability of success of such operation, which agrees nicely with the theory, which is 0.11. So the unitary fidelity, which couples the mode on the input and on the output, is a bit higher. But in the quantum experiments, we are mostly interested in the logical operation. So this fidelity is of more interest for us in the future. So our latest research is regarding the technology is to scale up this thing. So we're trying now to build the device with 8 modes on the input and 8 modes on the output. And also it has 56 electrodes. All this is fitted into the 100 millimeter sample. So before the quarantine began, we wanted to test it, but had no option to during the quarantine. So we are restarting these experiments now, and probably will have some interesting results regarding this technology during the upcoming months. Okay, so as the summary for this part, we have the femtosecond laser writing technology, which sits in our lab. It is quite good in terms of propagation loss. And also we can implement phase shifting using thermo-optical effects. And also we have a very strong collaboration, as I said, regarding the silicon nitride platform, which is being developed in Bauman Moscow State University. Okay, so now we move to the design part. So here we mostly work on designing the interferometer structure, which will be more prone to fabrication errors, since we have not the very best technology here in the lab, and the architecture of interferometer should tolerate the imperfections imposed by our technology. Sorry. So we want to build an interferometer which will cover the whole unitary space, connecting the input modes in the output modes. And the second question is how to design this unitary to fulfill the optimal probability of the quantum gate, which we want to implement using the interferometers we defined in the previous question. So we first start with the first question and then move on to the quantum operation. Sorry. So this is once again the topic we're discovering. So the purpose of this research is mainly to tackle the near-term architecture of the optical quantum computer, which can implement tasks like variational quantum eigensolvers, for example, which actually doesn't require any particular set of gates to be implemented. They search through the space of states and find the state which optimizes some kind of problem, for example, minimizing the energy of some molecule or some other compound. That's why the optical circuit, which is used in such experiment, should cover the whole unitary space, thus allowing to reach any particular state to probe this minimization objective. Okay, so the classic examples of the unitary decompositions of the device are depicted over here. So the one called the REC scheme was proposed in 1994 by a group of Anton Zeilinger. It uses this triangular mesh of beam splitters to implement the unitary between the input modes and the output modes. It was further improved by a group of Jan Walmsley. So it usually is referred as Clement skin in the literature. It is more symmetric, thus it is more prone to some losses inside of the circuit. And also it is important to note that each cross here inside of the mesh on top and the mesh on bottom is actually the Mach-Zehnder interferometer, which parameters are theta and phi. So this picture is taken from this work. It's actually important to note that the decomposition developed in Rex scheme was known long ago in this mathematical paper. So yeah, maybe we can find something else. So the problems with these decompositions is that once the Mach-Zehnder interferometer over here doesn't have the balanced beam splitters inside, the quality of operation strongly diminishes. So here we have the example of how these schemes, particularly the Clement scheme, works when we bias these beam splitters composing the Mach-Zehnder interferometer. So leaving the details off, the operation is depicted here on the picture on the left. So this is the histogram of the fidelity, which is obtained by running a series of simulations with numerical optimization of the circuit, given that the beam splitters are somehow biased from their ideal state, the balanced state. So as we can see, if the imbalance is quite high, the average fidelity that you can get using the circuits of the Clements kind shifted towards lower levels, whereas we want something around fidelity equal to 1 over here. So what we actually have done, we have developed an optimization procedure which samples the random unitaries using a quite simple algorithm. And then we use some kind of architecture, which I will speak further, to test its performance for sampling the random unitaries and to fit in them with the parameters of this architecture. So we built the fidelity histogram as the evidence that our circuit is capable of reaching any given unitary with some particular precision. So what we tried first was this quite naive generalization of the balanced beam splitter, which has n ports on the input and n ports of the output. The phase shifters are spread between the layers over here. We did not really know about this architecture much when we thought about it at first time, but then we discovered like a series of similar topics. For example, one of them is over here in the reference. But no one actually have done the proper analysis of how universal the skin might be. So the general decomposition looks like this. So the unitary of the interferometer is written by this letter lambda. The phi, the large phi, are the phases. The V's are the mixing layers over here. So these are the matrices mixing the modes on the input of this mixing region and on the output. So we did test different configurations of these matrices. The first one was the most obvious one, also the generalization of the balanced beam splitter, the Fourier matrix, which redistributes the light from the input evenly between the output ports. So we expected it to work quite good. So these are the histograms for the Fourier gates. The yellow color shows the optimal number of layers when you have the exact number of the parameters to describe the unitary group in your interferometer. So on the left, there are histograms for the less amount of layers in the interferometer. They don't perform quite good, but when you have the exact values for the number of parameters in the interferometer, the convergence of our optimization algorithm was almost perfect given the precision of the computation. So here we have just like one bin around the fidelity equal to 1. So we did this for quite large numbers of the dimensionality of the interferometer. So this is basically the number of input and output ports. And during this work, we found quite strange behavior. We tried to simulate what will happen if we imbalance a bit our Fourier layers. And it turned out that even if we imbalance the Fourier layers just to be some random mixing matrix, this behavior with quite good approximation of the given some arbitrary unitary with interferometer still works. So we can place not the Fourier gates in the middle of the layers, but also some random mixing layers, which are actually really some random unitary matrices. The only requirement for them is to mix the modes on the input. So for example, the permutation matrices won't work good because they don't really mix anything. They just relabel the inputs and outputs. Yeah, so this is the main result of this scheme. So you can really relax the requirements for the fabrication purposes for these layers which are mixing the modes, and you will still get quite good performance regarding the generation of arbitrary unitary matrices describing your interferometer. So this is the precision. You need to set the phases of this interferometer to get the results from here. So the precision is actually quite reachable in the experiment. So this is the precision in bits, and this is the fidelity of the operation of the interferometer. It looks like 8 bits is more than enough to fit the interferometer perfectly. And the modern experiments, they actually use the programmable controllers with up to 14 bits, I think, or maybe 16 bits, which is more than enough to fulfill the requirements. So the next tag was a little more classic thing with 2x2 interferometers in between. So here we have an irregular mesh, a regular mesh of the beam splitters with the phase shifters covering this mesh in a bit different fashion than, for example, in the Clement scheme. So here we have the Mach-Zehnder interferometers with the defined positions of these phase shifters, whereas in this geometry we simply have the phase shifters distributed between the beam splitters, not the interferometers. So the advantage of this circuit is that the light redistribution happens a bit faster. So we have different paths for the light to come from one input to another output, whereas in the Clement scheme, for example, coupling the light from the first input to the last output has only one possible implementation. So this makes this scheme a bit more robust for the beam splitter imbalances, which is shown right here. So this is actually quite the same experiment. I mean, the numerical experiment. So we have sampled a large number of unitary matrices and tried to fit the phases of the interferometer to meet the required precision of approximation. So the MTI-based curve shows how the Clement scheme performs, and the blue curve, BS-based, is the architecture which was shown earlier on the previous slide. It can be seen that the operation of this BS-based approach is more tolerant for the imbalance of the interferometer given here in terms of the angle, and also it is more prone to losses on each beam splitter, whereas the MTI-based is a bit less prone to the loss. So N here is the dimension of the interferometer. So this work is published over here this year. So summarizing this part of the talk, we have developed some circuits to tackle the problem of experimental fabrication of the given unitaries. So we are now trying to implement this error tolerance circuit depicted over here. And also we have plans to try that multi-mode scheme using our femtosecond laser technology and employing the approach of building a waveguide lattice, which couples the light and creates these mixing layers using the evanescent fields of the waveguides. Okay, so the last part is the gate optimization. So here the goal is to find the unitary of the interferometer, which is called lambda here, which gives the desired transformation in the dual rail encoding. Actually, it can be any other encoding, but the dual rail encoding is used is more widespread in the linear optical quantum computing in the contemporary experiments. So that means that we need to optimize the probability of success operation of the gate inside a subspace of the Fock state given here and on top. So the general scheme of the experiment might look something like this. So we have photons on the input, which are encoding the logical states. We also have the input logical states. We also have the ancillary photons, which help to enhance the probability, for example, and serve as the triggers on the output. And also we can add as much vacuum ports as we want. So the linear optical network in between is just a linear interferometer. We can tune it, so we can set any arbitrary unitary in our numerical experiments. So on the outputs, we have an array of the detectors with the coincidence measurement setup, which tells us which signal in this subspace of the Fock state we are receiving. And given this signal in this coincidence measurement, we can decide which state is on the output in this computational subspace on top. So the goal is to optimize the linear optical network in such a way that some triggering signals from the coincidence measurement give you the best probability to find the state which you want, or to implement the gate on the input logical states also in the desired fashion. So a bit of theory, the interferometer operation is described by this unitary matrix coupling the input creation operators and the output creation operators. The input state is the Fock state, so this one is the computational part, this is the ancillary part, and this is the vacuum part. The dimensionality of this Fock state depends on the number of modes in the interferometer and also on number of photons which we send into this interferometer. So the output state will be given by this simple equation over here. The omega here acts on the Fock state, and it depends on the lambda, which is the unitary matrix of the interferometer according to this equation here. So once we detect k photons in each of the measurement modes, this one over here on the right, the output state will be given by this partial scalar product with the appropriate normalization. So this A might either tell you which output state you have, or you may tailor the say to implement a particular gate if you have, for example, a subspace which you want to transform using your linear optical network into the same subspace on the output. So this task may be reformulated in terms of polynomial equations. So we just relabel the formula on the right with the polynomial on the creation operators. And we can do that also for the output state and for the target state we want, because it is just the notation of the formulas which everyone is familiar with. So then the problem is formulated like this. We need to find the alpha is the probability that the output polynomial G is equal to our target polynomial Q. So this problem can be further dissected into the system of polynomial equations on our matrix elements and on alpha, which in principle has the solution, might have the solution, which can be found using the well-known Grobner basis technique. But the problem is that computing the Grobner basis is a very complex computational problem, which lies in the X-space complexity. And even for a very small circuit with up to 10 modes and like up to 4 photons, we can find the configuration which doesn't really allow us to compute this Grobner basis on our computers which we have in the lab. And if we want to scale it somehow, it will be particularly impossible because of this X-space complexity of the algorithm. So regarding this problem, most of the groups working in this direction have other approaches. For example, we can construct some function which optimizes both the probability of the output state given some ancilla, and also optimizes the fidelity. So this part is the fidelity of our target state given some answer. Oh, sorry, there is a mistype here. So there should be not the ancilla, should be output state over here. So we basically compute the overlap of the output in the computational part of the circuit with some target state we want. And also we compute the probability to find this output state with the corresponding ancillary state, given that we have our circuit denoted by lambda over here. So for example, this can be done for 2-qubit Bell states, which is what we have started with. And also have you can transform this problem into finding a target gate. So if you, for example, want to transform the given subspace, for example, the 2-qubit subspace, which holds 4 Fock states for the logical states, so you need to optimize something like this for all the states in the subspace, and also you need to get rid of the states which don't lie inside the subspace. But right now I will mostly talk about the optimizing for the states, so for the state preparation purposes. So what we have done in our recent work is looking for the circuits of 3-photon GHZ state generation. So in the 3-qubit basis, the GHZ state is written like this. So when you rewrite it in the Fock basis, defining some 2 modes for each qubit, it will look something like this. So these are the Fock states which we are looking for. So the motivation of looking particularly for this type of states is that the 3-photon GHZ state depicted over here is a basic building block for the ballistic model I showed in the very beginning of the talk. So the known results, the best known results for this type of the problem over here. So the 6-photon 10-mode circuit can deliver the probability of success 1 to 256 if you don't have any possibility to send the feed-forward signal and to switch your circuit to meet some requirement. And if you have this possibility of feed forward, then you can increase this probability to 1 out of 32. I actually forgot to place the link here, but this work has been done by Terry Rudolph like around 10 years ago. So we have formulated our problem in the following. So we have the main optimization problem and the auxiliary optimization problem. So the main optimization problem basically fits our circuit to meet the state overlap between our target state T, which is the GHZ state, and our transformed input state. And also it optimizes the probability of finding the given ancilla over here using our circuit U and the given input state Cin. And also we have an auxiliary optimization problem, which helps us to reduce the number of elements required to construct the optical circuit. So it basically takes the theta I and phi I variables from the Clemens decomposition and tries to shift them towards the trivial values of 0, for example, to pi. So this is the diagonal part of the transformation over here, which is also shifted to the trivial one. So what we have in the very end is the circuit like this, which looks quite complex at the first sight. The probability of success is 1 to 54, and we managed to reduce the number of non-trivial beam splitters over here to, I don't remember really exactly the number, but around 12 or 15, if I don't, but we can count them further. Also, we can rearrange the modes a little bit to make this circuit look less complex. So in the rearranged transformation, the circuit looks like this. It actually has two almost identical parts on top and on the bottom, with the difference of the given phase shifters over here. And then there is a circuit on the right, which actually relabels the modes and does two Hongo-Mandel-like interference patterns over here. So the first three and the last three modes are our computational basis, and the four modes in between serve as a trigger. So the triggering signal for this kind of circuit is a three-photon coincidence. So we have a three-photon coincidence, for example, between the violet, cyan, and yellow modes, or violet, cyan, and black mode. And each of these patterns gives us a three-photon GHZ state in the 6 modes on top and on the bottom of the circuit. The structure of this omega block is right here. So this work is published on arXiv and is accepted to Physical Review A and about to appear soon. So at the very end here, I would like to advertise a little bit our numerical calculation package for the linear optical simulations. So we have developed quite fast code written in C++ to compute, for example, the permanence of the matrix and also the transformations of the linear optical device. And also it has a quite nice Python wrapper, which makes it easy to use without any compilations during the operation. So there is a GitHub link over here. So at this point, I would like to thank you for the attention, and I'm waiting for the questions.
Okay, so Ivan, thank you for a nice talk, very interesting. So please, questions, just raise your hand in Zoom. And I forget to say that you may download the slides of this talk from the Zoom chat. Okay, so questions, raise your hand, please.
Yeah, Paolo.
Okay, hello. So thank you very much for the nice talk. I have 2 or 3 questions if I don't take too much time. So the first question is concerned to the fabrication facilities that you mentioned. So are these facilities, these fabrication facilities, concerned only the research, or somebody else could order something from this fabrication people there?
You mean this one from Bauman Moscow State University?
Yes, yes.
I think they are not focused on the research solely, so I'm not sure if there is someone from their group in the talk right now, but I think you can.
I'm here. Ilya is here.
Yeah. So the director of the center, Ilya Dyakonov, is here in the talk. So I think that they accept any collaboration, given you have insufficient funding or something like this. He can answer.
Maybe Ilya will answer.
Yeah. Maybe Ilya will answer the question.
So as I understand you correctly, the question was about if we are working only with laboratory technology, or we can fabricate something more or less in Syria. And our center was planned and to be able to fabricate some devices in a very low very low volume of production. So we are not only research facility, but also fabricate some our products in small volume.
Okay, but would somebody like us could have a small circuit from you, something? Like,
yes, we can discuss it separately.
Okay, all right, thank you. So I have a second question. Is my connection was down when you were talking about this NB splitter approach? Could you please explain again? Because I was
which one? This one,
yes,
or
this
the next
one.
Yeah, this one.
Yeah, this one, NB splitting layers. So what are these parallel interferometers for? So you have single photons in superposition of these paths, or how could you please tell us again?
Yeah, okay. So the more or less understandable version is over here. So you just have an optical interferometer which has an input modes and an output modes. They are connected between each other using these beam splitters, using some kind of mesh over here, which is basically a two-mode device at each intersection over here. So this circuit is a sort of a generalization of the balanced beam splitter because it mixes the modes on the input and on the output using this mixing layer in between the phase shifters. So the red things are the phase shifters. So the mixing layer in between is some kind of a device which redistributes the energy between the modes on the input to the output modes. So it can be, for example, a waveguide lattice with evanescent coupling. So the light impinging inside this lattice traverses through the lattice and redistributes between the modes, for example. It also can be some kind of multi-mode interference device, which are typically used in lithography, for example. And the whole circuit is basically another take on the interferometer architecture. If you want to implement some particular unitary, you may either take one of these meshes, or you can create something like this, depending on the tolerances you have in your laboratory setup or fabrication facility.
So just one more question. I would like to hear your opinion about how competitive this linear optical for quantum computation can be as compared to other platforms.
Yeah, okay, a very good question. Surprisingly enough, the PSI Quantum does not provide any publications or something on their current research. But if you visit their website, they're actually claiming a 1 million qubit machine with error correction for logical qubits. I actually don't know how do they plan to do that at the moment, because we are only starting this kind of research now, because it requires a lot of technological challenges to be met. But regarding the pros of the linear optical technology is that I mean, the biggest advantage is that the technology itself is actually developed by industrial companies which are really not concerned about the optical quantum computing. For example, IBM or Intel have their own silicon photonics platforms, which are being constantly developed, and you can apply the developments from those fields directly to the linear optical quantum computing platform. The main obstacle here is actually these 3-photon GHZ states inside, which is quite hard to generate. So at the moment, there is, I would say, no source of 3-photon GHZ state on demand. There are some approaches to create these 3-photon GHZ states using the quantum dots, for example. There is actually Nicholas Amaski here in the talk who can comment a bit more about the quantum dots. Also, there are approaches to multiplex these 3-photon GHZ state sources devised with the circuits, the linear optical circuits as shown in the very end of the talk. But the further, it's actually quite hard. Okay, so also the linear optical devices have less decoherence properties, I think. So the photons really do not interact with the environment that strong compared to the superconducting circuits. And also in this architecture over here, the problem of losses is actually solved quite neatly because the photon, each photon from this 3-photon GHZ state should traverse only a fixed amount of beam splitting elements. There is a paper by Terry Rudolph, like 4 years, which was out 4 years ago or something like this. He estimated this number to be around 15 beam splitting elements and something like 6 phase shifters. So you need to really meet the low loss operation for the fixed scale circuit, which makes the approach right here quite more feasible because you can relax this very stringent requirement for the photons to travel from the very beginning of the circuit to the very end. Because now you just have to make your photons pass through a few beam splitters and tolerate a lot more error, a lot loss rate or something like this. So the approach is quite different. It's quite hard to compare it, for example, to IBM or Google, who are following the more conventional path, I would say, because this device operates in a probabilistic fashion at first sight, but the architecture of this device allows you to overcome even the probabilistic type of gates used for the fusion, for example, over here. So it's really like very hard to compare, but the Psi Quantum are quite confident about their success.
Okay, thank you very much.
Okay, so Dr. Xiaoson Ma, please.
Oh, thank you, Ivan, for this very nice talk. So I have several questions. First one is about the detectors you mentioned in the beginning part of your talk. You mentioned that you have installed like 24 detectors, and I assume they are all for 900 nanometer light?
Yeah, so they are optimized for 925 nanometer to work with our quantum dot source.
And how good they are? I assume 925, probably the efficiency could be very high, like
so
above 90%.
Yeah, the efficiency is above 95%. We did a rough estimate, but probably we will do a better measurement in the following months. But it should be above 85% or something. Maybe some of them are even above 90%. Okay,
that's very good. Are they from Professor Gossman's group or from other?
Yeah. So they are from the company Contel, which was founded by Professor Gossman.
Oh, okay. Okay. Yeah, that's very good. So the second question is about you mentioned that you would like to use, or you have used already, to use ablation technique to deposit electrodes on your femtosecond laser writing waveguides. And my question is, first of all, like the power consumption of this type of structure and the crosstalk. I noticed that you Can you say it again? Yeah. Power consumption and crosstalk about your electrodes.
Okay, so I missed a part of the question because of bad communication, but regarding the power consumption and the crosstalks, yeah, the crosstalks are the very issue of the devices like this, because the electrodes themselves are quite large, and also the overlap between the heating region and the mode running through the device is quite small. So we need to heat it up quite significantly compared to the thermo-optical devices made with the lithography, for example. So in our first experiments, we had something like half a watt per the heater for the 2 pi phase shift. And in the more recent ones, in the recent devices, we have something like 0.1 watt for each heater to induce the pi shift, not the 2 pi, but the pi shift. So we're building it a bit more optimized for the operation with large amount of heaters, like on this picture here. We didn't really try to make this device work at the moment, but according to our considerations, it should work nicely.
So do you consider any, like, for example, like to cut the crosstalk in such a dense circuits?
So there are approaches to cut the crosstalks. So you can, for example, fabricate the isolating trenches between the waveguides, which will prevent the heat from going from the heated region towards some other arms of the interferometer. We have not tried that yet, because the circuit of this size is quite complex on its own for our technology. So what we tried to do, we tried to reduce the width of the heaters, and also we tried to optimize the length. As you can see here, they are a bit wobbly. They have this wave-like shape to follow the path of the waveguide in order to make the length of the region where the arm of the interferometer is heated as long as possible. So the main direction of the crosstalk is actually across the circuit in the transverse direction, not in the one along the length of the sample. So the crosstalk across could be minimized by making these electrodes thinner. So now they are something like 30 microns thick, and the distance between these ports, as we can see, is around 125 microns. So in different parts of the circuit, that could be quite different. For example, in these junctions where the waveguides come closer to each other. So yeah, the crosstalks is the thing, but that's why we have developed the optimization procedure to fit this device to the given unitary. We did not do that so far, but yeah, at least we can try to do something with the classical distribution at first time.
And for the hardware implementation, you mentioned you use independent. I hear you correctly.
Sorry, I didn't
use okay. Do you use independent current source for controlling these electrodes?
So yeah, we have the programmable current source with 48 independent channels, I think, but it can be like extended, or you can remove ports on demand. So it's a home built device. I don't know.
Yes.
So there are available on the market, but they are actually quite expensive. So they cost like around $12,000 or something like this.
Okay, thank you. So we also suffered from the. So we used to use voltage sources, but it's not as good as independent current source. So that's one from the electronic part. And we also, as I mentioned 2 weeks ago, we also suffered from the thermal crosstalk, but that's something we have to deal with no matter what. Yeah. Okay. Thank you. Yeah. So yeah. Thank you.
Okay. Thank you for questions. And we also have a question in the Zoom chat from Nicola Samaski. Could you, may you ask directly?
Yes. Hi.
Yeah, please.
Yeah, hi.
Thank you, Ivan, for the very interesting talk. Actually, I have one question related to the circuit for the generation of the GZ state.
Yeah, just a second.
I didn't get if that is already based on the mesh approach or is based on the standard Clemens one design.
Yeah, so this one right here is based on the Clemens decomposition because it was easier to use that decomposition for the optimization purposes. But once you have the unitary, you can decompose it into any possible interferometer architecture. But here, yes, the decomposition was made according to the Clemens paper. So the original one, this one. So,
okay, so you have also room to reduce the circuit depth?
Yeah, it might be possible, yes. But we did not do that at the moment. So this is just, so in this approach, we tried to reduce the number of these non-trivial beam splitting gates and the phases. So as you can see, most of them are just the crossings or.
Device 1 connect.
Yeah, so if you disentangle it, you just have something like this, which is way simpler than the picture before. But yeah, you're right. If we use some other approach to the interferometer design, we can probably reduce the circuit depth, for example.
Okay, thank you. Then the second question is about the GZ state generation probability, where you said you have the difference between the feed forward, active feed forward, or without the feed forward. There, in an experimental case with thermal phase shifter, what is the threshold speed to actually have real feed forward and therefore reduce the getting to the higher generation probability?
So yeah, nice question. Thank you. For the feed forwards, you actually need quite fast switches and also some kind of the delay line, which will help. Which will help your computational state in this top part of the device to live throughout. You make the coincidence measurement, you make some calculation, you send the signal to the circuit, and all this takes time. So you have to store this state on top in some kind of optical memory. It might be a resonator or a delay line, just a long waveguide or something like this. So the thermo-optical phase shifters, as far as I know, don't operate faster than several hundreds of kilohertz. I think this is the limit imposed by the physics of the device themselves. So the kilohertz operation, even the 100 kilohertz operation rate, is something around a microsecond. So storing the optical state for a microsecond, I think, is almost an impossible task. Because, as you know, 1 nanosecond is somewhere around 30 centimeters. Yeah, so a microsecond would be around several hundreds of meters probably, which is impossible to fit onto the circuit. The delay line this long. So you need to use an electro-optical device to implement the switch, which operates quite fast in the nanosecond range. Because, for example, current delay lines or current resonators can store the light for something like a few nanoseconds, maybe.
Right, so you really need nonlinear elements.
Yeah, so non-linear elements for the linear optical network. You mean for the optical network, for the gate, or for?
Well, that's a tricky question because you said if I have to use memories to store my state to do active feed-forward, then if I have efficient memories, then I use them for deterministic gates.
So I was talking about the linear optical implementation of the memories.
Yeah.
Just yeah, of course, if we have some very efficient non-linear device which can implement, for example, the quantum memory or the 2-qubit gate, even with not optimal entangling power, that would sufficiently enhance the whole structure. Yeah, that's for sure.
So active feed-forward is far to implement so far for the current technologies available around internationally. I mean.
So yeah, so implementing the feed-forward on the chip would be quite challenging. There were works implementing the feed-forward on the optical table. I think Akira Furusawa and quite old work by Anton Zeilinger and Philip Walter were concerning this kind of things. But on chip, I have never seen something like this before.
Okay, thank you very much.
Thank you. So Ranjit, please.
Thank you for your talk. I have two questions, quick, I suppose. So first question is, in your presentation, you are not using polarization properties of photon. So is there any reason?
Well, there is no particular reason. In fact, the interferometers written on any architecture over here doesn't specify which modes we use. So you can use waveguide modes, as I was telling during my presentation. But for example, this work in the bottom of the slide elaborates the scheme like this using frequency modes. So these rails here are mapped to some frequency beams, which are manipulated independently using a special light modulator and some frequency device. You can also use polarization as a separate mode, but you will need to implement the mixing layer over here, keeping in mind that the polarization degrees of freedom should also be mixed with each other. So actually, this decomposition doesn't make any assumption on the nature of the modes, on the nature of the device you use. So if you have something with the polarization, you can certainly use the polarization basis to enhance your work.
Thank you. Second, I suppose, quick question. Do you plan to use a mix of linear and non-linear optical elements?
Yeah, thank you. So most of the work in linear optical quantum computing is done with the single photons. So as far as efficient non-linear gates and non-linear systems working on the single photon range will not be available like to the lab, like for example our quantum D source, which we bought from the Quandela company. We probably won't use non-linear elements. So the non-linearity has to be very efficient to work on the single photon level, and the systems like these are usually engineered specifically for these purposes. For example, the quantum dots, but these are like quite rare cases, and they're quite hard to operate. And making, for example, the single photon source accessible on demand, like buying it, took around like 10 years of research for these guys. And at the moment, the non-linear gates operating on single photon level are not available.
Thank you.
Okay, Alexander Frolov, please.
Thanks, Ivan, for the talk. I have a technical question. It's interesting, how do you usually realize the coupling between initial single photons and waveguide printed by femtosecond laser?
So the coupling between the photon source, like actually any light source.
Initial photons and waveguide.
Yeah. Okay. So
is it? Do you use special devices, or it's just usual? Maybe it's lens.
Yeah. Okay. So for the femtosecond laser written chips, there is actually not much problem because the optical mode of the waveguide is almost the same size as the optical mode of the fiber. So if you just butt couple the fiber to the waveguide, you will have something around 1 dB per facet at our wavelength. So this is just the specific, the particular operation of our femtosecond laser writing device. So we have managed to find the regime where the core has the refractive index matching the refractive index of the core of the fiber. So if you are talking about lithography-based devices, then the situation is more complex because here the mode confinement inside the waveguide is actually sub-wavelength. So we use structures 600 nanometers wide and around 200 nanometers tall. So we have to fabricate, well, we have to design, and the Bauman Moscow State University have to fabricate some kind of mode converters. So these are either the grating couplers, which are used like in most of the lithography-based devices, and the edge couplers, which are the tapers. So this is the waveguide, which gets narrower to the end of the chip. That's making the mode larger, and making the mode larger makes it matching with the fiber on the inputs. So we don't use any specific fibers at the moment because we want to operate with the devices using several ports, for example, 8 ports or 16 ports or even more. For example, on this photo here, we have an array of waveguides on the input and on the output. And for example, if we want to use lensed fibers, which typically used with edge couplers, we need to somehow fabricate this V-groove layout with the lensed fiber. And so as far as I know, it's quite a challenging task to put this lensed fiber in the V-groove, such as the tips of these lensed fibers sit at the same distance from the facet of the chip. And that's what you want if you want to have equal coupling between the chip and these lensed fibers. That's why at the moment we use regular waveguides or regular fibers, sorry.
Thank you, Ivan.
Yeah, and of course you can use any kind of lens or objective to couple, but you just need to match the modes.
Okay, so are there any more questions? Looks like not. Okay, in this case, thank you all, and see all of you next week. And thank you again, Ivan, for the nice talk.
Thank you for listening.
Thank you. Bye.
Thank you, Ivan.
Well, see you next.
Yeah, see you.
Goodbye.
See you.